We've seen exponential functions before, but in 7.7 we're going to get a little bit more into depth into what makes an exponential function either grow or decay. And that's our only objective. Again, model exponentially either if it's growth or decay. And one more time, an exponential function can model growth or decay of an initial amount. Just depends on a certain part of that function. We'll take a look back at that function itself. Exponential growth can be modeled by this function we've seen before, y equals a times b to the x. A's got to be positive, B's got to be bigger than 1 if it's growth. And the base B is what we call the growth factor, and it's going to be 1 plus the percent rate of change expressed as a decimal. Again, if that's when you're given the percent rate of change, we can find that. But we've seen that function before, a times b to the x. Looking at those parts again, that number in front, a, that just means the amount that you start with. So your initial amount when x is equal to 0. Remember, for any exponential function, we always raise x as our exponent. And that second number, b, that's going to be our base, which as long as it's bigger than 1, we're going to see that that's going to be a growth factor. So we have an example of exponential growth graphed off to the side, again, just with kind of any growth in general. Again, it is important that b has to be bigger than 1. We'll see what happens when it's not. But as long as that's true, if our growth factor is bigger than 1, we're going to see our function start to expand as I keep going. So we're given this in form of a word problem, trying to fit that with our function of exponential growth. Suppose that in 1985, there are 285 cell phone subscribers in a small town. Number of subscribers increased by 75% each year after 1985. And we want to use that to figure out how many cell phone subscribers there were in the small town in 1994. I'm going to cross the last part out. We don't have to worry too much about the monthly cell phone increase. We're going to look at that in a second, but let's focus on how to rewrite that information as an exponential growth problem. So first of all, I highlighted a few things from that question itself. 285 is important because that's our starting value or our initial amount when our x is 0. So in our exponential growth function, that's going to come at the start of our formula. 285 is the value that we start with, so that's the value we put first. And then if I'm told that the number of subscribers increased by 75% each year after that first year, that would be our percent rate of change. And again, if I used a decimal, 75% would be 0.75. I can't just use 0.75 as my equation, because remember, if I'm writing this growth factor, it's 1 plus the percent rate of change as a decimal. So that's where that 1.75 is coming from. I start with 100%, or I start with 1, and then I add that 75% onto it. So that gives me 1.75 instead of just 0.75. So this is the formula that we're using. 285 cell phone subscribers that I start with as my initial value. Increasing by 75% each year is multiplying times 1.75. Again, it's got to be a number bigger than 1 if we're using growth. And we're using x again as our exponent. So we actually have to find how many cell phone subscribers were there in 1994. We're basically just figuring out how many years was that since our starting number. Since we're given this data in form of years, 1985 and 1994, just got to do a little subtraction off to the side, figure out how many years that would be. So that would be 9 years if I find the difference between those two. And the only thing I have to do now is take that value for 9 years. I can substitute in for x in my function. And 285 times 1.75 raised to the 9th power, if we enter that into our calculator, should give us about 43,872 subscribers. So again, that's taking a value that we know, 9 years, plugging that in for our variable. That's 1.75 raised to the 9th power, and that should get us our total. So we can see this also in the form of interest. If we see this in finance, you see a bank pays interest on both the principal on the and the interest an account has already earned. The bank is paying what we call compound interest, so paying both the original amount and the interest that's been added on. Compound interest is an example of exponential growth, and we can see that with our graphs as well. You can use the following formula to find the balance of an account that earns compound interest, and this again is the big formula. A lot of pieces to that formula, and a lot of the work is just describing where those pieces come from. So capital A, I'm going to refer to that as the account balance, so that's how much we have in our account. Capital P is the principal. Again, that just means the initial deposit, the money that you start with. And notice the connection to the exponential function. Initial deposit comes in front, just like our first value, 285, that came before the parentheses. So always going to start with our starting value outside our parentheses. Then inside our parentheses, just a little bit more complicated in terms of our growth factor. If we're finding an interest rate, that's going to be our R. That's the annual interest rate expressed as a decimal. So something like 75% interest would be another 0.75. And if we're doing something we call compound interest, we're going to take that interest rate and divide it by n. And n refers to the number of times the interest is compounded per year. So let's say if I did it every month, that would be 12 times per year for n. If I did it every day, that'd be 365 times for n. Just depends on how many times you're compounding it. And we're also going to involve t in the formula. T is going to be how much time we're compounding this for in terms of years. So I think this is going to make a little bit more sense once we see some actual values. Again, this is just the equation in general. Once I see some numbers for it, we're going to get that in the form of a word problem. So a word problem is saying, suppose when your friend was born, your friend's parents deposited $2,000 in an account that pays 4.5% interest, and that interest is compounded monthly. So we want to figure out what will the balance be on my friend's 18th birthday. So all I did to start with is just copy that same formula from the last page. Again, this is account balance. We have our principal, we have our interest rate, we have our times compounded, also have the number of years. So first thing is to figure out how much information is that problem telling us. First thing that I highlighted, if I deposited $2,000 in that account to begin with, that's what we would call the principal. That's the money that we start with in our account. And that, again, when I substitute that in my formula, it's going to come before the parentheses. So I substitute that in for P as that 2,000. Other parts of my formula, I'm always going to have a 1 plus my percent rate of growth. So start with that 1 plus in our formula. And for the interest rate, if I say 4.5% interest, you've got to express that as a decimal. So 4.5%, that'd be 0.045. So got to express that as a decimal, and that'd be the numerator of my fraction in that formula. If I compound monthly, again, that's describing what our n was for the formula, is how many times do we compound it per year. Since there's 12 months in a year, that would be a value of 12 for compounding monthly. And notice we use n twice in the formula. We use that as the denominator inside your parentheses, so I use that for that fraction. But we also raise it to the nth power, so n is going to be part of that exponent. So we have 12, and last part missing in that formula, if it's my friend's 18th birthday, we've been compounding that interest for 18 years. So time in years, that'd be 18 to finish our formula. Again, all you got to do is substitute all those parts from the word problem, $2,000 that we started with, 4.5% interest is 0.045 as a decimal, compound that 12 times per year, so I divide it by 12. And then when I use my exponent, again, it's n times t, so that's 12 times 18. Basically, that tells you how many times total was it compounded. You could take a step to simplify it, or really you could also enter it from the very first equation already into your calculator. But 1 plus 0.045 divided by 12 gives me a little bit bigger decimal, 0.00375. And if I do 12 times 18, we're raising this 216 times that it's being compounded. Again, all we're doing from here is entering that into the calculator. 2,000 times this decimal raised to the 216th power gives us 4,489.01 to the nearest cent. So our value does double basically over the course of 18 years, and we did that with our compound interest. So that was an example of exponential growth. If I'm paying money to an account, it should be growing over time, not losing money from keeping that in the bank. But we can also use that same exponential function, y equals a times b to the x, and we can use it to model exponential decay instead of exponential growth. And in both cases, again, b is still determined by the percent rate of change, but the value of b is going to tell us if it's growth or decay. So we still have the same exponential function. Again, it's still a times b to the x. Big difference here, though, is that our growth value, if it's decaying, b is not bigger than 1. It's actually a fraction or decimal, so it's in between 0 and 1. So in this case, if b is less than 1, we call that, instead of a growth factor, it's called a decay factor. And instead of saying 1 plus the percent rate of change, we're going to say 1 minus the percent rate of change for our decay factor, since we're subtracting that from 100%. So same formula, a times b to the x, still the same pieces. A is still your starting or your initial amount. Base is your decay factor, but remember this time it's just in between 0 and 1, so you just want to think it's less than 1. And if I have my decay factor, so if I have a fraction or decimal that I keep multiplying by, we're going to see that these numbers keep getting smaller and smaller. They keep approaching 0. So I will have a decay graphed as my exponential function. Let's try that with a word problem. So again, this starts out as the kilopascal, unit of measure for atmospheric pressure. We start with an atmospheric pressure at sea level about 101 kilopascals. So for every 1,000 meter increase, though, once we go up in altitude, pressure decreases by about 11.5%. Important word there now is that we're decreasing, not increasing. And we also want to use that to find the atmospheric pressure at an altitude of 5,000 meters. So again, starting with that same formula is still a times b to the x. means we got to figure out a starting value first. And that starting value is what they tell you at sea level. It's going to be 101 for your pressure. So we're going to say our A factor is 101, and again, that just comes before your parentheses in your equation. And then if your percent rate of change is 11.5%, remember for our decay functions, we're going to have to subtract that from 1. So 1 minus that percent expressed as a decimal gives us 0.885. Again, we know that it's decay just by looking at this equation because that value for our B term, what I have inside those parentheses, that's less than 1. It's not greater than 1. If I did 1 plus that percent rate of change, that would be an increase. So that would be a growth equation. So we have two pieces that are important to start with. We have our starting value, 101. We subtracted 11.5%, so that left us with basically 88.5% every time. And last thing left is to figure out how many times am I using that decay factor. And this question is a little tricky. If it increases every 1,000 meters, and if I'm measuring at an altitude of 5,000 meters, I don't want to just substitute in 5,000. I take 5,000, divide by every 1,000 meter increase, I should have basically 5 increases. So that's what we're going to use as our exponent. I use that decrease 5 times. So if I raise that to the 5th power and punch that into my calculator, should give us 54.8. And again, those units would still be kilopascals. So one more question to look at, and again, that's why we use our decay rather than our growth. Why do we subtract the percent decrease from 1 to find the decay factor? First of all, we got to subtract it, not add it, because we want to decrease and not increase. And also we subtract from 1 because 1 represents 100% as a decimal. Same thing with our very first question, when it was growth, we still added on to 1. We started with 100% and then just added 75% for a 75% increase. So the only difference if we're looking for decay is I don't want to add that percentage, I just want to subtract that percentage. So 1 minus that same rate of growth, that gives us 0.885. And since it's less than 1, I can tell just by looking at it that would be a decay and not a growth. So make sure you have these notes down, and we'll work on some of that practice together in class.